Hey everyone, this is FixReef, and today we have this Kessil AP700, a huge light that was released a few years ago by Kessil, supposed to be fairly powerful, sort of combines in itself a couple of regular Kessil lights inside, and just a very big light, barely fits into my camera view. So this light came in with the problem that it does not turn on. Otherwise, it looks in a very good condition. You can hardly tell that it's been over a tank, extremely clean on both sides. So I doubt that's a corrosion issue. So let's open it up and see what's inside. All right, so the panel comes off pretty easily. Now we'll need to figure out how to open up um, the rest of the slide. And so this is how you disassemble an AP700. Quite a bit of a pain, primarily because they put all of this adhesive in here that that's holding things together. But now that I have disassembled it, I think I already right away see a problem. But before we get to the problem, let's go over what we see here. So, two LED clusters, obviously. It looks like 6 channels per LED cluster. What else is here? So, very familiar components to other Kessil lights. The way they've assembled this light is very interesting. There is actually a promotional video on YouTube somewhere from Kessil showing how they assemble these lights at the factory, and it looks really nice and all. And from that video, you can see that somebody, when they put everything together, somebody goes in with a soldering iron and solders all of these pins on both sides to the main board, potentially after they've already put it into the heatsink, which I thought was kind of odd, but that's what they do. This, of course, creates all kinds of challenges for us because, you know, I don't know what's on the other side of this board, but if I wanted to work on this board outside of the heatsink, I would now have to likely desolder the LED clusters first on both sides, and only then can I get the main board out. So quite interesting. But now on to the problem areas. Okay, so it looks like the main controller is here. Everything is of course coated in protective silicone coating to prevent oxidation, but we can see this white hue over here. Something badly damaged, all burned out over here, and also this appears to be badly damaged too. So this component and this component have been fried. Let's zoom in on what they are. This and this. I do not know exactly. It looks like there is a component here that's similar to this. I don't know if these are sort of identical. I'll have to take a closer look. And this is completely gone. Wow, it's completely, entirely gone. Well, that would explain why the light is not working. But first, before we move on, we have to find out what these two components are before we can claim that we should be able to repair this unit. Alright, so start with the easy part. This is that one component that has a corner damaged. You can see what I would like to do is I'd like to find out what that component is. So we're going to remove some of the coating on top and look up the markings. Looks like a 66M AJJS at the bottom. That's probably a date code, but that P12 at the top is what I can make out from all of the damage. Okay, so that little thing turns out to be an RS485 transceiver that apparently Kessil uses in this particular light for communication. Obviously that's busted. This thing over here is a voltage regulator that's also busted. So when the voltage regulator goes like this, it concerns me greatly because the regulator is supposed to take in higher voltage and turn it into lower voltage. If it burns and shorts like this, it's possible that it managed to send or had enough time to send high voltage to something that requires low voltage. And judging by the components surrounding it, those are all very low voltage, 3.3 volt, 3.2 volt controllers. And if the main controller is busted, we're going to have a problem. So first, let's remove bad components and find out if there is a problem with the existing components that have not been badly damaged. This moves pretty good, so it probably burned through the traces. That's going to be fun to deal as well. So for those of you wondering, I have seen a few of these lights before with very similar problems, and that's how I know. But when the components are so badly damaged, I can still tell what they are because I have seen previous lights with different problems where these components were not damaged as bad. I can actually see if I can make out the value on this. There is still some markings left. It does look like it says 7533 on it. 33 likely stands for 3.3 volts. And I realize, of course, that you can't see any of it. So yeah, this is the logo. And then 7533. That's what's supposed to be in here. You can tell that, hopefully you can see this, but the pads are moving slightly, so the last bit that's left is the pad underneath. It probably welded itself to anyway. Alright, I'm gonna try to break it out into pieces. Okay. Now we only have the middle pad. And it's definitely welded itself to it. Well, while we're at it, let's also remove the communication chip as well. The concern that I have right now is that the communication chips are usually not the ones that go bad by themselves. So it probably got burned because the voltage regulator got shorted. And it probably received those, 20, 30, whatever, 40 volts that went through. And if that is the case, it's also feasible that the main controller received the same voltage. And if it did, we're going to have a problem. But we're about to find out. The only thing that's holding it now is conformal coating. and off it goes. Okay, well, this one doesn't look too bad at all. It will require some cleaning before I can put a new component in place here, but it does not look bad at all. First, let's test the area around the voltage regulator. The data sheet is pretty straightforward for it: ground, voltage input, voltage output. So ground to input, no short. Ground to output, completely shorted. And this is bad news. This is bad news. Output is shorted at this point to ground. So what I'm going to do while I'm under the microscope is I'm going to attach my test wires. I'm going to have a voltage injection implemented here. So I'll take a couple of wires. I will attach them to the output. So I'll give it very, very low current on the output on 3.3 volts. And I'm going to see what warms up. But there is clearly a short. The D14. Okay then, let's remove the diode. The diode looked suspicious from the beginning. It had its some kind of gray coloring on top, but I wasn't sure if this was just from the voltage regulator blowing up. Very odd. Oh yeah, look at this. Yeah, it's definitely bad. It's probably a common diode used in Kessels that I have seen plenty of them failing in previous generation lights. Let's quickly review the damage and what we've done so far. Well, so far we have the buck converter over here that's shorted. We have this voltage regulator here that provides 3.3 volts to controllers over here that's also pretty much gone at this point. We've removed it. A diode is missing. And this communication module is also missing because we just removed it, as it was also significantly damaged. A couple of issues of interest. So in order to investigate what else might be broken here, let's take a look at what else this board is feeding. So we have, let me zoom in, we have a few wires over on this side that are actually connected to this. So there is a 12 volt, well, there's a fan ground and PWM. This is the fan connector over here. I've tested this fan connector with just 12 volt, well, maybe 10 volt input, and the fan is working fine. So that's a relief. That means that the 48 volts that made it all the way into this area didn't make it into the fan, it didn't damage the fan. We also have 12 volts over here, ground, and something called A and B. Now this A and B are actually related to this controller over here that we just removed. So this is feeding elsewhere, and of course the 12 volts are going elsewhere. It turns out that all of this is now feeding into this little board over here. You see the red wire 12 volts, the black ground, A and B, but also 3.3 volts, more ground, and a few other wires over here. So these wires lead towards the buttons that are on the, on the side of the slide, and these wires lead to something else. Let's find out what these wires lead to. Unlike this board, this one's easily removable. There's just a couple of screws. As you can see, that there is a Wi-Fi module on top. And when I removed the covers from this light, there is actually an antenna that's connected to this Wi-Fi module that I had to snap off before removing the cover. So now with this removed, oh, wait a minute. So this is the USB board. I was under the impression this is just the USB, and maybe A and B are leading over here from the USB, but we have more than that. Let's take a look closer at this board. So on this board, there is actually the main controller is right here. There is a communication chip. That's another one of just the one that blew up. And we have some significant damage over here. Oh, that's wonderful. So there's more damage. Okay, so on this board, we have the main controller. There is already a chip over here, and there is a chip over here that is damaged. There is a damage on this guy. It burned out. All right, let's take a closer look at what it is. So from the circuitry over here, one can guess that this is some type of a voltage regulator or buck converter, because you have an inductor, you have capacitors here, a couple of resistors. This is some type of a voltage regulator. This is, what I'm guessing is that the input of 12 volts, this is where it gets converted into 3.3 as well to feed everything that's on this board. And it's damaged. So we'll need to find out what it is, see if we can find a replacement. So let's get under the microscope. Actually, before we get under the microscope, let me show you another problem. So poking around this earlier, I realized that A and B are completely shorted. Just like that. So it turns out that A and B relate directly to the pins on the communication controller that we just removed. And in fact, right here, if I touch these two, I end up with two shorted pins. That's not how it's supposed to be. These are the communication pins, and they're not supposed to be in that short. The reason they're in that short is because that communication module talks to this communication module over this blue and yellow wires. And so, let me see. And indeed, they're shorted also over here. So this tells me that this module, when it's shorted, it also shorted this module. So this module will have to be replaced for sure. So let's get, it's actually a good thing because now we can find out which module that is exactly over here. And we also need to figure out what this is. So let's see here. This is, I just removed the coating. This is the same VP circuit that we've seen before. So this is the RS485 or whatever that is transceiver. That's the VP. Texas Instruments VP12. And this guy is busted. So we know what it is. We'll have to replace this one as well. Now let's look at this. Oh yeah, this has a hole in it right in the middle. Let's zoom in and see if we can get the reading. Oh, I think I recognize this. There is a D over here, a K with two dots. Yeah, this is the Rigtech voltage regulator or a buck converter, I suppose. Small one, real small one, adjustable. Kessil loves those. They have this running on other smaller lights for providing power to fans, I think, and so on and so forth. What happens here is that I bet, so this is the input. This is where it burned. This is where it's supposed to get 12 volts. It got 48 in here, so that's where it burned. This is the output going to the inductor, and this is supposed to be where the feedback, I think, loop, which is the one that does the adjustment of the output voltage, and that's done by these two resistors over here. So, and some other things here. So that's what it is. So that's what this guy is. I think I have some of these resistors. I think I have some of these voltage regulators in stock. So we're just going to go ahead and replace this one right away, because my concern is that, there is so much damage in voltage regulators all over the place, and these voltage regulators are providing 3.3 volt power to controllers. If we have too much damage on controllers, there is not going to be a good reason to save this light. Controllers are very difficult to come by. So I'm just going to go ahead and replace this voltage regulator, power just this side of the circuit, and see if we're going to be able to at least power this side up, maybe the buttons, a couple of LEDs here, just to indicate that the controller is working. Okay, let's just do that. It's just completely coming apart. Well, now you at least know what the inside of the voltage regulator looks like. Okay, now that we have it out, let's get a brand new controller, or the buck converter. And let's roughly put it in place. Well, need some solder. I need some flux. Okay, first of all, I positioned it wrong. Should be more like this. A little messy, but we'll clean it up. So now to test this, I'm going to just connect 12-volt input from my lab power supply to the red and black wires, and just watch what's going to happen on the other side. Let's see if it smokes. Here comes 12 volts, and it's immediately shorted. So we do have a short. So it appears that the short might actually be coming from this controller, which would make sense because the Wi-Fi module has its own controllers. So let's remove the Wi-Fi module. Alright guys, here's what I have done so far. To trace down the short that we have on this voltage regulator, I figured that the problem is likely with the Wi-Fi module because this was the general area that was heating up as I ran some current through it, but nothing was really hot on the board itself. So I ended up removing the Wi-Fi module. First off, in case you're wondering, this is what that Wi-Fi module looks like. So this is the other side of it that kind of goes over here. Nothing particularly amazing here, but definitely a few components. And then there is this side. There is a shield that I had to remove. And underneath I found this very familiar ArrayLink chipset. This is a very common, very typical chipset for Wi-Fi modules. In fact, something very similar, same brand, but maybe perhaps, if not the same type of chipset, was used by AI Hydras. Except that, those Wi-Fi modules were actually designed for AI Hydra by another company just for their lights. These ones you can actually buy online, just the entire chipset. So I'm not sure if I'm going to repair this. I was just curious about what's inside of those. But I actually have a few of these ArrayLink chipsets for Hydras. I'm curious if one of them will fit, and if not, I'll just use a new module. But guess what? When I attempt to run current through this guy, right away, ArrayLink chipset heats up. You should be able to see it even with this. Right there, starts drying up in the middle. Everything else is wet, and this heats up right away. So this chipset is gone. Luckily, we should be able to replace the Wi-Fi module fairly easily. All right. So let's start figuring out the main board for now, and we'll get back later to the Wi-Fi board. So far we have the voltage regulator and the communication controller. There is something peculiar. Well, there's something interesting about the voltage regulator here that I don't really like. Again, remember that we have ground. Well, I guess you can't see much. So remember that we have ground, voltage in, voltage out. This is supposed to produce, I'm guessing, something like 3.3 volts from the input voltage, but the maximum input voltage that it can handle is only 24 volts. The actual input into the light is 48 volt, double that. So something else is supposed to bring the voltage down so that it's safe enough for this controller to function. And that something is yet another buck converter that's sitting over here. You can kind of see the familiar setup. There is an inductor. There are some capacitors here. There are a couple of diodes. So this one is supposed to take in very high 48 volts and bring it down to something else. What that else is, I don't know yet. However, let's test what we get at this point. Okay, so here is my voltmeter, and I'm going to test the voltage at the input for this converter. And it's showing my 48 volt input. So this is not reducing this. And by the way, there's a T7 at test point 7, which is supposed to help you test for the voltage here, and it's showing 48 volts, which means that this controller is not, or this buck converter is not doing what it's supposed to be doing, and that is take the input 48 volt and bring it down to a safe, whatever it is, 12 volts or 5 volts, but it's clearly not doing anything. This buck converter is one of the annoying types that combines the MOSFET inside. The MOSFET might have shorted here, and it's just pumping direct voltage out. Might also be the reason why this voltage regulator eventually failed, because it just can't handle 48 volt input. So there is a problem with this buck converter that we need to investigate. So I'm going to get under the microscope, and I will test a few things. All right, so hopefully you can see this guy. Again, it's covered in conformal coating. We don't have to worry about it for now, but so it's one of those hard to find buck converters that takes very high voltage, up to 60 volts, I believe, 50 some volts, and can make it as low as 3.3 volts. Again, it's got a built-in MOSFET inside, which is usually an annoying thing, because once they're usually not the greatest quality, and when they fail, the whole thing fails. Looks like it's moving fairly good, but conformal coating is likely holding it in place quite a bit. And that's why I say that it destroys them. It destroys them. Okay, we got it out. And the reason I need to remove the conformal coating everywhere is because of the heatsink. If I keep the edges covered in conformal coating, it's not going to sit well. It will still connect to the pins, but it's not going to sit well. And if it's not going to sit on top of the heatsink, then it's not going to conduct heat, and it will fail eventually. Now let's take a brand new buck converter. See how it's got this, it's got the heatsink pad underneath. So let's take that, a bit of flux. Alright, it's moving real good. It means that the center heated up, and also attached to the heat pad. Okay, so let's test for some intermediate results. At this point, I will plug it in shortly, and I should be able to see 12 to 13 volts output from this buck converter. I'm going to let it cool off a little bit, as it's quite hot, and we'll test. Power on, ground, T7. And look at this, 13 volts, just like expected. Okay, we fixed our first problem. But this is by far not the last problem. So now we have 13 volts input at the next voltage regulator. I'm going to test it once again right at where the pin is, and my multimeter is showing 13 volts. So this is good news. The next step is going to be installing the voltage regulator. So I'm going to get under the microscope. We'll have to fix it we'll have to put an effort to fix it because it welded itself previously onto that onto the board, and there's quite a bit of damage to the traces. A lot of this pad exists here for the purpose of heat dissipation as well, so I want to preserve as much of it as possible. Most of the area took solder very well. Let's suck it all out. Alright, look, the pad looks real good now. Let's put just enough solder. That's good enough. You can kind of see that one of the pins is gone and it's been damaged. It's not that big of a deal to have it gone, and I will explain in a minute. So here's why we don't have to worry about this pin being gone, or the trace for this pin being gone, because as you can see, the heat sink pad and this pin connect together. So as long as we have power on the larger pad, we don't really care about whether or not we have something on the pin. So let's put this this little guy in. Went in just like the original, nice and easy, because we cleaned it so well. So as my replacement, I'm going to use this Schottky diode. Need to just position it properly, and for that matter, maybe add a little bit of solder. Perfect. Okay, now that we have the next voltage regulator in place, or what I realized, it's actually another buck converter that takes the input 13 volts and converts it into, I don't know, 3.3 or 5 volts or something along those lines. I want to make sure that we don't have a short on anything. Looks like, well, this one's supposed to be there, but nothing on the output. Okay, let's test and find out if we get proper voltage reading at the output. The power is on, and once again, at the input, now we have 6 volts. At the output, we have 3.3. Last but not least, there is a communication circuit here that we need to replace as well. So let's get under the microscope and clean this up and put the new one in. This will presumably be much easier as there is no heat pad underneath. And it's just a matter of removing old solder, putting some fresh one in, and a brand new communication controller. My understanding is that this communication controller is used to talk to the secondary board with Wi-Fi module on it. So okay, I want to believe that I'm done with this board. I'm gonna plug it in one last time to ensure that nothing's smoking, nothing's blowing up, and the voltage is as they should be. The power is on. Let's check some voltages. Three 3.3, 2.2, and for some reason it just wants to be lower at the input 6 volts. Maybe that's how it's supposed to be. I don't know. But so far so good. Now I'm going to focus on this board. So obviously the Wi-Fi module is still missing. We'll need to install that. But before we install anything, I'm going to have to figure out what else I need to replace here. So if I remember it right, I already previously put a voltage regulator on here over in this little corner. I believe that that's the only one that was bad, but the Wi-Fi module turned out to be bad, and we'll need to repair that as well. Okay, so here's our little RF module. I already tested it previously and determined that the main RF controller is damaged and shorted, but everything else seems to be working just fine. So this turns out to be the exact same controller that is used on AI Hydras, and I have plenty of those to replace. So I'm just going to go ahead and swap this controller. So I just realized that I wasn't recording the process of removing the railing. I just got the camera rolling again, but what I've done so far is I've removed the BGA chip, got all the balls underneath here, and cleaned up a little bit this area, and removed some solder. I'm just going to go ahead and wick off the remaining solder. It actually looks fairly clean. And I also managed to knock off one of the capacitors here. So that guy needs to go back. All right, first let's make sure that that capacitor is properly seated. I think it will need some more solder. That's how it's supposed to be. And now let's make sure that all of the solder is gone from the board. This type of work you have to do under the microscope, because otherwise it's impossible to see these little BGA pins. And if you don't clean them up well, you're not going to be able to have the new controller seated. And you mess up potentially just one pin, and you're done. But under the microscope I can easily see if I missed any of the solder pins. And that's what it looks like. Now this area is ready, mostly, for the new controller. I'm gonna put a healthy amount of flux underneath and make sure that everything is covered. And to replace the original, I have this perfectly good, brand new railing. So I'm gonna use it as is without reballing. It's probably going to be unleaded solder balls, but okay. The best way to do this is to position it as perfect as possible, so that when it all heats up, it will just seed where it needs to go and be happy. This one I'm gonna go gently on because I don't want the controller to move at all until everything is warmed up. All of the balls, the board, and once it's done, it's gonna just gently dance under the... Okay, now it's not moving anywhere. That means that it's melting where it needs to go. And I think we got it. Well, now that I'm more or less confident in the Wi-Fi module, I'm going to go ahead and start reassembling the smaller board. First, this Wi-Fi module is going to go on the smaller board, so we'll need to clean up all of the solder from the mounting holes and get that ready. Okay, so I fixed up the wiring, fixed up the board. I'll have to seal all of this eventually, installed the Wi-Fi module, replaced the communication chip, and now it's time to, before I reassemble, it's time to do the initial test. Are we successful at least getting this light to turn on after all of this work and replacing so many parts? Let's find out. All right, the very first, power up. All right, I see the light is on over on the smaller board. Let's try to turn it on manually anyway. Ah, look at this. The light is on. I can hear the fan spinning. The light went from over here, it went from the smaller LED light went from red to green, meaning that it's on. And let's see if we can control it. Control the intensity. There's the intensity going down, almost to nothing. Now we can control the color. Excellent. Well, it looks like the light is working. This is excellent. So let's recap of what happened here. This is, after all of this work, this is, I think, what has actually happened to this light. Initially, the buck converter that's supposed to convert input 48 volts into 12 volts failed. And it shorted to the point where instead of producing 12 volts, it was always producing 48. There is no protection between the 12 volt output of this guy and the 12 volt input of this guy. So when 48 volts went straight into this buck converter, that buck converter blew up, took out a bunch of components, took out the communication controller that also runs on 3.3 volts, and that controller also took out the Wi-Fi module and the other communication controller that's on this board. Luckily, the rest of the light survived, which is a miracle. But after replacing all of these parts, replacing even the BGA Wi-Fi chip, it looks like the light is working now. Well, this concludes this repair. If you enjoyed this video, please like and subscribe, and I will see you next time.